AI systems don't just run on code. They depend on GPUs, model artifacts, vector stores, and training pipelines, each with its own attack paths. In this lesson, we'll secure the infrastructure that turns AI from experiment into enterprise system. So far, we've built the security stack layer by layer: identity, application, and API controls, cloud posture, and Kubernetes. Now we'll apply those controls to AI infrastructure itself, including GPUs, model registries, vector databases, and training pipelines. AI workload security begins with familiar controls, but the assets change. Training data, prompts, embeddings, outputs, and model weights all become high-value targets. Accelerators introduce hardware sharing, driver, memory, and scheduling risks. Model registries and datasets need provenance, signing, access control, and governed promotion. The key mindset is simple. Training pipelines, vector stores, and experiment environments are production systems, and they deserve production-grade security. In a shared GPU environment, isolation depends on every boundary between the workload, runtime, driver, host, and device. Risk appears when memory is reused without cleanup. Scheduling allows one tenant to starve another, or timing behavior exposes side channels. Drivers, libraries, and container hooks also expand the host attack surface. Treat GPU access as privileged, monitor utilization patterns, and alert on anomalies such as crypto mining, model extraction, or unexpected device access. When GPUs are shared, isolation has to be designed in, not assumed. A weak pattern is letting every team land in the same GPU pool and hoping requests behave. A stronger pattern uses separate node pools, namespaces, labels, taints, and admission rules, so only approved workloads can reach sensitive accelerators. Resource requests and limits reduce noisy neighbor exhaustion. Where hardware supports it, MIG-style partitioning adds another boundary by giving tenants smaller, dedicated GPU slices aligned to identity and data sensitivity. Containerized AI can make GPU access look like just another resource request, but the security boundary is thin. Treat every GPU-enabled pod as a hardware-facing workload. Avoid privileged mode, narrow host mounts, and remove unnecessary Linux capabilities. Run only trusted images with approved CUDA, ROCm, or vendor libraries. Protect device plugins and runtime hooks, because they broker access to the accelerator. Finally, monitor which containers are mapped to which GPUs, so unexpected usage becomes visible quickly. GPU abuse is often visible before it becomes a breach or a surprise bill. Monitor utilization, memory, temperature, processes, job identity, and ownership together, not in isolation. Correlate spikes with Kubernetes audit logs, cloud cost data, image provenance, and identity events. After-hours usage, unknown containers, long-running jobs, or unapproved images should trigger investigation. Your incident response plan should also cover GPU nodes, AI jobs, logs, artifacts, and owner attribution. The model registry is the security checkpoint between experimentation and production. Each model artifact should arrive with lineage, datasets, training code, parameters, metrics, owner, and evaluation results. Versions should be immutable, so teams can reproduce and audit what changed. Access controls define who can upload, approve, download, or deploy. As a model moves from experiment to staging, approval, and production, gates such as signing, scanning, evaluation, and review reduce supply chain risk. Every model artifact should be handled like a release candidate, not just a file. After the build, create hashes for weights, containers, configuration, and tokenizer assets. Sign them with a trusted key and store them with provenance. Dataset version, code commit, pipeline run ID, dependencies, metrics, and approval. Before deployment, inference, fine-tuning, or transfer, verify the signature and compare hashes. Tamper-evident logs and policy checks make unauthorized replacement visible and block unapproved promotion. Promotion gates make deployment a controlled decision, not an automatic handoff. Before a model reaches users, artifacts and dependencies are verified, vulnerabilities are scanned, and policies are checked. Quality evidence is reviewed as well. Benchmarks, bias results, robustness, and regressions against prior versions. Approval should separate builders from reviewers and operators, so risk is assessed independently. Production readiness also includes monitoring and a tested rollback path when behavior crosses safety or performance thresholds. Embeddings should be treated as protected data even when they are not human readable. Start by separating tenants, applications, environments, and sensitive classes into isolated namespaces or indexes. Encrypt vectors, metadata, and backups, and keep ingestion and query traffic under TLS. Most importantly, authorize the query before retrieval, so the database only searches what the requester is allowed to access. Log ingestion, searches, deletions, admin changes, and policy decisions, so investigations can reconstruct what happened. In secure RAG, vectors must carry access context. Each chunk should be tagged with tenant, owner, classification, source, retention, and access group. When a query arrives, authorization should narrow the searchable space before similarity search whenever possible. If filtering happens after retrieval, it must be mandatory and fail closed. Cross-tenant or cross-project searches need explicit approval and audit trails. Test with fake tenants, adversarial prompts, and restricted documents to catch leakage before users do. Consider a support chatbot connected to an embedding store built from company documents. If HR policy fragments are embedded with department tags and employee groups, retrieval can expose restricted context without showing the original files. The mistake is treating vectors and metadata as harmless indexes. Protect them like confidential data. Encrypt the store, minimize searchable identifiers, enforce deletion and retention, govern backups, and watch for bulk export, inversion attempts, and abnormal similarity probing. Training should be governed as a supply chain, not just executed as a compute job. Data should be validated before it enters the pipeline, features, and code should run under scoped identities, and the training environment should use pinned, verified dependencies. Every run needs enough metadata to be replayed: commit, dataset version, parameters, environment, seeds, and run ID. Finally, sign artifacts and publish only trusted outputs to the registry, with logs that prove what happened. Workload security is about controlling every place models run, move, and learn. Protect GPUs with isolation and monitoring, registries with provenance, vector databases with authorization, and pipelines with reproducibility and governance. Together, these controls form the foundation for secure AI across multi-cloud environments.